Chemistry, Paper 1, May 2023. Question 1. So we have to complete on here the number of subatomic particles in each of the isotopes of hydrogen, A and B. So we know that isotope A has got an atomic number of 1. Remember, the atomic number defines how many protons there are, so that will be 1. It's an atom, so it's going to have the same number of electrons as it has protons, and its number of neutrons, remember to find the neutrons, we do the mass number, take away the atomic number, so that's going to be 1, take away 1, which is 0. On to isotope B, the atomic number is 1, so there is 1 proton. There's going to be the same number of electrons as protons, and then to calculate the neutrons, we do the mass number, take away the atomic number, giving us an answer of 1. For the next question, we are given this graph here, showing that there's oxygen and hydrogen gas being used in the hydrogen-oxygen fuel cell. We can see that on the graph we have got a horizontal line going across here, and then suddenly it drops down to 0 at 75 minutes. The question that we asked is to describe what figure 2 shows about the voltage, or how the voltage of this fuel cell varies with time. Let me see if I can get the graph into the camera picture as well, just so that we can see it all together. So there's 2 marks available for this question. We're describing 2 different parts of the graph, so we're going to start with this bit. So you would get 1 mark for saying voltage stays constant for 60 minutes. So there's your first mark, and then your second mark, and then falls to 0 volts. You could add on to there between 60 and 75 seconds, but that's not required to get that mark. The key bit is describing the 2 sections of the graph and the relevant numbers. On to part C of this question. So we've got our electrolysis cell here, or our chemical cell, sorry. We've got 2 electrodes, we've got an electrolyte. Why must sodium and sulfur electrodes? Why they're not suitable for the experiment? And the first thing is, sodium is a very, very reactive metal. When you put that into water, it instantly melts and then starts reacting really vigorously, sometimes with flames and sparks. So your first mark is sodium would react with the water. That's it. That's all you need there. And for your second one, describing sulfur, why would sulfur not be appropriate? Well, sulfur is a non-metal, so therefore it's bonded covalently. And if it's bonded covalently, there are no charged particles that are free to move. So there's no delocalized electrons, and there are no free-moving ions. So simply, sulfur does not conduct electricity. And there's question 1. Question 2. In an experiment, powdered calcium hydroxide was added to dilute hydrochloric acid and the pH was measured. This is the one where we added the powder and it stayed acidic and it stayed acidic and it stayed acidic, and then all of a sudden it neutralized and then became alkaline. So we've got a rough method here. We have to say what will be done after step 2 to make sure that the reaction is complete. You could have any of the following things: stir, swirl, shake the beaker, or mix, or warm, or heat it. Okay. What you would not be allowed is something like wait for a long time or something like that. So there's your bit here. I know that when we were having a look at this, we were having a look to see whether it had neutralized. That doesn't give the best indication because some of the products, in fact some of the reactants as well, are insoluble as well. So it doesn't give you a full picture in this experiment. Then we had to complete the word equation for the reaction. So calcium hydroxide is our base plus hydrochloric acid. Remember that base plus acid makes water and salt. So water, nice and easy, and it's a word equation, so it's just the names. And then working out our salt, we take the first part from the base, so it's going to be calcium, and then it's hydrochloric acid. Hydrochloric acid always makes chlorides. So 1 mark for water, 1 mark for calcium chloride. Then we've got our multiple choice question. Which row of the table correctly shows the state symbols for powdered calcium hydroxide and dilute hydrochloric acid? Well, it's powdered, so therefore it must be a solid, so we're looking at C or D. And dilute means that it has been dissolved in water, so it must be aqueous, so therefore our answer is C. We've then got this graph, just like I described earlier. This is the graph that we produced when we did the core practical. And using this figure, we had to give the pH of the acid at the start of the experiment. So here's the beginning of the experiment. It's slap bang between 0 and 2, so therefore it must be pH 1. We then had to calculate, or to give, the mass of the calcium hydroxide required to make a neutral mixture. So this is the point here where the pH is remaining at a constant point. Is rising up here, so it's neutralized at exactly this point here, and we're looking here 0.74 grams for our answer, 0.74 grams here. And that's where you've got this vertical line here, where you've gone from acidic all of a sudden to alkaline, so nice and straightforward. Right. This one was answered not so well by a lot of people because we forgot to talk about the particles involved. So there are 3 marks available. The first mark is really nice and straightforward. So the first thing is saying that the solution is acidic or has a low pH, or, this is the most important one, a high concentration of H+. That's the most important thing here. That's what makes it a low pH. You didn't get a mark for saying it is an acid, because that's given in the question, but it is acidic. So there's your first mark. Your second mark for saying that it is a neutralization reaction, or for saying H+ plus OH minus goes to water, because that's describing a neutralization reaction, or for simply saying that H+ reacts with hydroxide. Third mark, and this is where most people dropped their marks because we have to say why it has gone to a higher value. The concentration of H+ has decreased. Or you could say the number of H+ ions has decreased, or the concentration of OH minus has increased. So hopefully that all makes sense to everybody. So this was the bit here, and it's important when we're talking about neutralization that we're referring to H+ and OH minus whenever we can do. Question 3. So we've got a reactivity series, so high reactivity to low reactivity, and we had to state which of these metals will react when added to cold water, and we're going for our most reactive one in the series, so calcium. We are then given some information here about investigating 4 different metals. So we add equal size piece to different test tubes, and we have hydrochloric acid in there. Notice it's dilute, so that means it's aqueous. And then we've got the recordings of the observations for zinc and for copper given here. So steady rate of bubbles, slightly warm, and no reaction for copper. What you had to do was to predict the observations, the reactions of magnesium and of iron with dilute hydrochloric acid. Remember, we've been given the reactivity series, so we know that magnesium is up here, and we know that iron is here, so it's above copper, and that the magnesium is above the zinc. So what are our marks going to be for here? For magnesium, you would get a mark for saying that many or lots of bubbles are produced. You could also have a mark for saying the tube feels hot or warm, or warmer than with zinc. You'd also have been allowed here as well, the magnesium disappears because it reacts so quickly. For your iron, you've got to be a little bit more careful. We know from the previous bit, if you remember looking back here, that zinc produces bubbles at a steady rate. So we need to be letting the examiner know that we know there's going to be not as many bubbles produced as that. So you're going to get a mark for saying that we're going to get a few bubbles, or bubbles are produced slowly. Or you could talk about the temperature change. You have to be saying that it is not as hot as the zinc one. Now, it said on the table that zinc feels slightly warm, so you have to have something that implies it's less. So you could have very slightly warm. That's important here. Just slightly warm would not be good enough, because that would imply it's exactly the same reactivity as the zinc. Or you could have the tube does not feel warm. Then we've got our old favourite, the test to show that the gas is hydrogen. 1 mark for lit splint, 1 mark for squeaky pop. We should all be getting those 2 marks every single time. Then we had to complete the balanced equation for the reaction. We know we've got magnesium reacting with hydrochloric acid, which hopefully we've all learned is HCl. Makes magnesium chloride and hydrogen. Remember that hydrogen is one of our diatomic gases. So we can put in our numbers here. So we're going to H2 on here would get you 1 mark for knowing the formula of H2. And then balancing it all out, we've got a 2 here to balance it. Part C. So we've got our excess of magnesium added to pH 2 hydrochloric acid, and we measure the mass of hydrogen gas that's produced, and then we repeat it with the same excess magnesium but the same volume of pH 1 hydrochloric acid. How many times greater is the concentration of the hydrogen ions in the pH 1? Remember that it's a logarithmic scale, so it's going to be 10 times greater. So pH 1 is 10 times greater than pH 2, and pH 2 is 10 times greater than pH 3, and so on. And then we had to have a look at the mass of hydrogen that is produced when the reaction is complete. At 0.005 for pH 2. If we've got 10 times the quantity of hydrogen ions, then it's going to be 0.05 multiplied by 10, which gives us 0.05 grams for our answer here for 1 mark. If you had got the wrong answer here, let's say you'd said it was 8, then you would get the mark here for multiplying 0.005 by 8 in this one here. So you would at least get your error carried forward for this. That's question 3. Okay, question 4. So here we've got some stuff about producing sulfuric acid in industry, and we've been given an equation here for making sulfur dioxide from copper sulfide and oxygen. And we had to calculate our atom economy for this particular reaction. So, first things to do, we had to work out the total mass on either side of the arrows. So let's have a look over here. We know that Cu2S is 159. and we know that O2 is 32. So if we add the two of those together, we end up with a total mass of 191. So there's your first mark for that. We then need to have a look at our atom economy. So remember, we are trying to produce sulfur dioxide. So we're trying to make the sulfur dioxide. And we know that the mass of sulfur dioxide is 64. So we've got a percentage calculation to do here. We want to find out what percentage 64 is of the total mass, so 191. Remember, it'll be 191 on each side of the arrow. And then we're going to multiply the answer by 100. And we have to give our answer to two significant figures. So if you do this sum, you end up with an answer of 33.507. And you would get a mark for doing this bit of the calculation. So there's your second mark. You get a mark for getting that. That's your third mark. And then you get a mark for converting to two significant figures, which gives you an answer of 34. So there's your fourth mark there for converting that to two sig figs. Okay, so we've got some vanadium oxide, V2O5, and we have to base it on the position of vanadium in the periodic table. And if you have a look at your periodic table, you'll see that it's in the transition metals. And remember, we know a couple of things about transition metals. First of all, they have high melting points. And secondly, they have coloured compounds. Vanadium oxide is vanadium bonded to oxygen, so that is a compound. So we're looking for a coloured compound, so it's going to be one of these bottom two, and the one with the high melting point is going to be our answer. So we want D for our answer there. Okay, on to the calculations then. So we've got our equation here for forming sulfuric acid. So sulfur trioxide plus water makes sulfuric acid. We had to calculate how much sulfuric acid we made from 400 tons of sulfur trioxide, and they've kindly given us the relative formula masses. So the first thing we have to do is to find out how many moles of sulfur trioxide we've got. Now remember that you can kind of ignore the units. You can just assume that this is grams here, and you end up with the same numbers in the end. So remember, number of moles is mass over Mr. So our mass here is 400. Our relative formula mass for sulfur trioxide is 80. And if you put that into your calculator, you end up with an answer of 5 moles. So there's your first mark there for that bit of your calculation. We then have to multiply that 5 by the formula mass for here, because we're trying to find the maximum mass. So remember that mass equals Mr. moles. Our MR for our sulfuric acid is 98. Multiply that by 5 moles. That gives us an answer of 490 tons. Percentage yield of sulfuric acid. So different amount of sulfur trioxide, so it's a different bit of calculation here. We have 700 tons is the possible amount that could be made, but we actually produced 672 tons. So again, it's a nice simple calculation. It's the actual yield divided by the theoretical yield multiplied by 100. So that's going to be 672 over 700 multiplied by 100, and that gives you a percentage yield of 96%. And then 2 reasons why the percentage yield is less than 100%. So this comes up so often. There's 3 possible answers that you could have. Incomplete reaction. So some of the stuff didn't react. Loss of substance or reactant or product. So it might be that some fell out, or that some was left on the sides of the container, or some was lost when it transferred from one thing to something else. All those possible reasons. And then your third one that you could have got was unwanted side reactions. So those are your 3 possible things. Question 5. Right, the balanced equation for the reversible reaction between nitrogen and hydrogen to make ammonia. We have done this so many times. We know it's going to come up in every single exam. So we know we have got nitrogen plus hydrogen. Remember, they are both diatomic. It's a reversible reaction, so it needs to have the reversible reaction arrow. And then the formula for ammonia is given to us in the question. And then when you balance it out, you get 3 of those and 2 of those. For your mark breakdown, you get 1 mark for having the correct 3 formulae. So N2, H2, NH3, 1 mark. You get 1 mark for balancing it, so that's the 3 and the 2 there. And 1 mark for this. That's a terrible arrow, isn't it? For that arrow there, the reversible reaction symbol. So 3 marks for that balancing equation. Then we had to say what the temperature and pressure are for the Haber process. So remember, it's a really, really high temperature and a fairly high pressure. So we're looking for D here for that one. Learn your conditions. What's the purpose of the iron? It's a catalyst, or you could say to increase the rate of reaction, which is what a catalyst does. And then part 4, you had to explain how the position of this equilibrium changes if temperature is decreased. We are told that the reaction gives out heat, so remember that an equilibrium system will try and undo the change that's been done to it. So if it gives out heat and we have decreased the temperature, it's going to keep making more heat, or giving out more heat, to say rather, to try and undo that change. So you're going to have a mark for saying it moves in the exothermic direction. You could have a mark for saying it moves right or towards the products. Or you could have a mark for saying to oppose the temperature reduction, or to release heat, increase the temperature. And then the last part of question 5. This one people struggle with a little bit. I don't massively love the mark scheme myself, I have to confess. So we've got our compound A, which is dark brown, our compound B, which is colourless, and we're told it's a reversible reaction. We've got our sealed glass tube containing the equilibrium mixture of A and B, beaker, a kettle, and some ice. And we know that at room temperature, it's a pale brown colour as a mixture. And we have to come with an experiment to show how the position of equilibrium is affected by the temperature without opening the tube. So, mark number 1. Put the tube in hot water. You were not allowed to have put it in some steam or put it in the kettle. Mark number 2. Put the tube in cold water or ice. So those ones were nice and easy. And then the 3rd mark was for describing what you would expect to see. So you would get, say, in 1, the colour would go darker, and in the other it would go lighter. You could have drawn a diagram to show that as well. This one you could only get that mark if you had scored marking points 1 and 2. So you couldn't get any marks talking about colour changes if you hadn't talked about putting it in hot water and then putting it in cold water. So that's question 3. Question 5, sorry. Question 6. Okay, so we've got a mass of Copper produced when copper chloride solution is electrolyzed using inert electrodes. Everyone's favourite topic. Here comes the electrolysis question. So, where is the copper formed during the electrolysis? So remember that copper is a metal, so it's going to have a positive charge, therefore it's going to go to the negative electrode, and hopefully we can all remember cations are positive, and that's going to therefore go to the negative electrode, which is called the cathode. We've then got a 3-mark question which says to state, so to say what it is, and then to explain the trend. So, your first mark was for stating what the trend is, as current increases, the mass increases. Nice easy mark. I think most people got that one. Here's where we didn't do as well. There are all sorts of explanations that really missed the point of this. So your second marking point is for saying because at higher currents there are more electrons, and if you're doing it properly, flowing per second, but actually you just got the mark for saying there's more electrons. And then your third mark was for saying so more copper ions, or you could have just said Cu2+, are reduced. You had to have the word ion in there if you didn't give the formula. You could also, as I have said lots of times, just use the half equation, Cu2+ plus 2 electrons goes to copper. That's also going to get you mark number 3. Remember, for the electrolysis questions, always write the half equation out. Okay, part 3. Describe how, after the power supply has been switched off, the mass of the copper formed can be measured. So remember when we did this, we measured the mass of the electrode before, then at the end of the experiment we rinsed and dried the electrode, and then we measured it again and subtracted the difference. So here's where your marks come in here. The first one was for dry the electrode. Drying because you could still get a fairly valid mark if you just took it straight out of the electrolyte and dried it. You might have some impurities on there, but the point is here you're getting the mark for understanding that if you just have it in liquid and take it straight out, there's going to be drips still on it, which will affect the mass. Mark number 2, measure the mass of the cathode or the electrode. And then you would subtract the original mass, but you didn't need to do that to get the mark. So some people wrote things like weigh the electrode at the start and the end. That's absolutely fine, you get the mark for that one. Okay, an Avogadro's constant question. So we had to calculate the number of copper atoms in 74 milligrams of copper. We've got a units trap here to be aware of. And we're told the relative atomic mass of copper and Avogadro's constant. So the first thing that we needed to do was convert 74 milligrams of copper into grams. Remember, a milligram, milli means 1,000, so a milligram is 1,000th of a gram. So the mass equals 74 divided by 1,000, which gives us 0.074 grams. So there's your first mark here, converting your mass. Next, we had to calculate the number of moles. Remember, moles equals mass over Mr. So that's going to be 0.074 divided by 63.5, and that gives you an answer of 1.165 times 10 to the minus 3 moles. Then you have to calculate your number of atoms. So we're going to remember that 1 mole contains this number of atoms. So all we do is we multiply these two together. So our atoms equals 1.165 times 10 to the minus 3 multiplied by 6.02 times 10 to the power of 23. And that gives you an answer of 7.015 times 10 to the power of 20. So how do you get your marks? There's 1 mark for doing the mole calculation, so that's mark number 2, and then your third mark is for this bit. Or if you got that number, you got all 3 marks. There were then some marks available for various bits and pieces, such as forgetting to convert would get you some marks still for doing some of those calculation parts. Question 7. Okay, so we've got ammonium nitrate being made by neutralization, and you had to state the name of the 2 reactants that are neutralized to make the salt ammonium nitrate. Remember, ammonia and ammonium are different things. Ammonia is NH3. Ammonium is a compound ion or a polyatomic ion, which is NH4+. So, what are our 2 reactants that we need? Well, the first one is to make a nitrate. Remember that we need to use nitric acid. And then you had 2 possible options that you could have had for this one. You could either have ammonia or ammonium hydroxide for your second mark. So one of those 2 for your second mark would be fine. Okay, so on to fertilizers. We've only touched very briefly on this so far in our lessons, but fertilizers usually contain nitrogen, phosphorus, and potassium for the things that plants need. But the question here is what elements are combined in the ammonium phosphate. We've already talked about what ammonium is, so that's NH4+. Phosphate is not an ion that you need to have memorized, but remember that that 8-bit means that there's oxygen in the formula. So there's going to be some phosphorus and there's going to be some oxygen. So we want nitrogen, hydrogen, phosphorus, and oxygen. So therefore we have got D for our answer. Okay, here is a bit of titration work then. And you can see the start of the titration and the end. You can see the meniscus here. And you had to calculate the volume of solution that's been added from the burette. So the first thing was that you had to do some readings here. So we've gone from down here from 1.4, and it's in between the 4 and the 5, so that's going to be 1.45. And here we're going down here, so we've got 27.567 and a bit again, so 27.75. So there's a mark for getting both of those readings. And then you had to subtract the 2, so 27.75 minus 1.45 gives you an answer of 26.3. But because both of the values given in the question are to 2 decimal places, your answer should also be to 2 decimal places. So your first mark was for working out both of these 2. Your second mark is for this number here. 26.3 was not to a suitable number of decimal places because it wasn't to the same level of accuracy, so you wouldn't get the second mark if you only wrote 26.3. Okay, we've got some results here to have a look at, and we had to tick the ones that we would use to calculate the mean volume. So remember, we never use the rough one. That's just to help us to be working out, so we don't want that. And then we wanted the 2 values that were within 0.1 centimetre cubed of each other. So therefore we're looking at these two because these two are within 0.1, so we want that one and that one to get the mark. This one's an anomaly, it's too far away from them to be useful for us. Okay. So this question was pretty badly answered. I think it was just people not quite reading what the question said. So students written this description, how they would use the burette. You were to give 3 improvements on how they used the burette. So it had to be referring to the burette in your improvements. So mark number 1 was for rinse the burette with either water or the solution that was going to be in it. So there's our first mark on that one. Second one, we needed to fill the tip. Remember, you need to run the tap so that the bottom part of the burette was filled with the solution. So that's this bit here. That needs to be filled. Otherwise, when you start running out, you're going to lose some of your volume just filling up this part. You could get another mark for saying, let's just put some bullet points here. Do not fill the burette over 0 centimetres cubed, or you could say run the solution out below 0 centimetres cubed. Or your fourth mark was for add the solution drop by drop near the end point. Those of you who wrote about swirling the flask, using a white tile, all those sorts of things are not the use of the burette, and that's why you didn't get the mark for it. Okay, this question's horrible. I really hate it, and it caused a few issues for some people. I think what they're trying to do is test, do you know your colour changes, and just stick it all in one mark, which seems a little bit unfair, but there we go. So we have got some alkali in the flask, and we've added some indicator, and then we've added acid to neutralise it. So essentially you need to know what are the colours of litmus and phenolphthalein when it's an alkali. So we know that litmus is going to be blue, and we know that phenolphthalein is pink. Now, I am of the opinion that if you have something that is blue and something that's pink mixed together, you're going to get something that is purple. So luckily, they would also have allowed you to have purple as an answer. But no other combinations really would be allowed. Pinky purple would be all right, bluey purple would be all right, or just purple. And then when you have these two indicators in acid, litmus goes red, and phenolphthalein is colourless, so it's not going to affect it, so it's just going to be red. So we're looking at blue, pink, or purple to red for 1 mark. A mean question. Part D. They rinsed out the flask with distilled water and didn't dry it. So that's the flask, not the burette. They used the flask for titration, adding the solution until the indicator changed colour. What effect, if any, on the tighter volumes, that's how much is used from the burette, of using the wet flask rather than a dry flask? So if I just bring up the diagram here, you would put your alkali into here, and you'd have measured out exactly how many centimetres cubed of that you've got, and that's going to carry a certain number of moles of alkali. And that number of moles of alkali is not affected by any water on the inside of this, because the number of moles isn't changed. And then when your acid runs in, it will react with that number of moles of alkali. We're not recording the speed of the reaction here. we're just recording how much is needed to react. So actually, any water on the inside of the flask would have absolutely no impact on the reaction here. So what effect? No effect. So there you are. Question 7. Question 8. Copper sulfate is made by reacting copper oxide, which is a base, with dilute sulfuric acid. Remember, base plus acid makes water and salt. Copper sulfate is the salt. What's the other product? It's the water. Right, so we are adding our copper oxide. When it's stirred with black powder disappears and you get a pale blue mixture. You add more copper oxide and so on and so on. How did the student know when to stop adding copper oxide? So there's 1 mark for observing something, and then there's 2 marks in here for saying why that happened. So your observation, you stop when some powder is left at the bottom of the beaker. Nice and straightforward. Right, then you have to talk about copper oxide and talk a bit about the acid. So at this point there is an excess of copper oxide. Had to have the word excess there. And then talking about the acid, all of the acid has been neutralized. And then the multiple choice question. So what's the best way to obtain crystals of copper sulfate from an aqueous solution? So if it's aqueous, that means it has been dissolved. So filtering would not work, so it would pass straight through the filter funnel. Heating the solution until dry doesn't work because you don't actually get crystals and it spits everywhere and it's really dangerous. Heat the solution using a water bath, which is the gentle heating with the evaporating basin over a beaker, or leave it in a cold, damp place. Well, that one's absolutely ridiculous. Our correct answer is C. Question D. So when we've removed some water, we get some crystals of copper sulfate. We describe how the arrangement and movement of the particles change as the crystals are formed in the solution. So you've got to talk about the solution and the solid. So I'm going to just break it down into 2 halves. So the solution, ions are freely moving. 1 mark. Ions are randomly arranged. 1 mark. Solid. Ions are fixed or vibrating or not moving. 1 mark. Or ions are in a lattice or giant structure. So 4 different ways of getting your 3 marks. Just make 2 points about each one of them. Ions are freely moving, ions are randomly arranged. Ions are fixed, ions are in a lattice. You were allowed to make 1 mistake with the name of the type of particle. So we've got ions here. You could have allowed to use particles because ions are a type of particle. If you used molecule instead, it's completely wrong because molecules are only when you've got simple covalent bonding. If you used molecule at any one point, you'd be allowed to have that mistake once. You wouldn't get any more times where you referred to molecules. So you are limited on that. But ions should be the correct thing. We know it's ionic because it's copper sulfate, metal, and a non-metal. Question E. Explain in terms of electrons whether the copper in copper oxide has been oxidized, has been reduced, or has not been oxidized or reduced. Let's have a look at the two things. So we've got CuO and we've got CuSO4. Now, we need to be thinking about the charges on all of the things in here. So this is nice and straightforward. We know that oxygen is in group 6. You can check your periodic table. So oxide has got a -2 charge. So that means that the copper in this compound has to have a 2+ charge so that the charges are cancelled out. Copper sulfate. Well, if you've learnt your polyatomic ions, you know that sulfate has got a 2- charge. So that means that the copper must be copper 2+. So actually, the charges haven't changed at all in our copper. So therefore, there's been no movement of electrons whatsoever. So let's have a look at our mark. 1 mark for saying neither oxidized or reduced, and your second mark for saying they haven't gained or lost electrons. And you had to have both those things in there. You couldn't say they haven't gained electrons, and you couldn't say they haven't lost electrons. You had to say they haven't gained or lost electrons for that second mark. Okay, we have got a concentration of 39.875 grams per decimeter cubed, and we have to calculate the mass of the copper sulfate that is dissolved in the 300 decimeters cubed of this solution. So remember that concentration equals the mass divided by the volume. So if we're going to rearrange this, we're going to be multiplying both sides by the volume, so we end up with mass equals the concentration times by the volume. So therefore we're going to have 39.875 multiplied by 0.3, giving us a mass of 11.9625, or a number that rounds there, so 11.96 would be appropriate as well, or 11, or even 12 would be fair enough as well. So 1 mark for that. Question 9. So we have got this lovely molecule of compound S. We had to deduce the empirical formula of compound S, and it really was as simple as counting how many of each of the elements that are in here. There were some good people on here who actually, you could see they've been crossing them off as they counted, and if you worked it out, you ended up with C6, H8, N2, SO2. And there's no way that we can simplify that any further because there's only one sulfur atom in there. Remember, the empirical formula is the simplest ratio. That is the simplest ratio of the elements that are in that compound. Okay. Which of these is pure or impure, and say why you think that is. So 1 mark for getting the correct one. So B is pure, A is impure, C is impure. Okay, so there's your first mark. Okay, so impure, pure, impure. Your reasoning: B is pure because it has a sharp or a single melting point. You are also allowed to have fixed or specific or definite or one or exact or no range, not precise. For A and C, you got a mark for saying their melting points are over a range. So there we go, there's our 3 marks for that one. And then we've got some chromatography here. We have been told that compound S has got an RF value of 0.22. you had to calculate the distance moved by the spot if the solvent front has moved by 2.4 centimetres. So remember, RF equals the distance moved by the spot divided by the distance moved by the solvent. So then we have to rearrange, so multiplying both sides by the solvent distance. So the spot distance equals the RF multiplied by the solvent, which is going to be 0.22 multiplied by 2.4, giving us an answer of 0.528 centimetres. Okay, 6 marker. I know you all love the 6 markers. So we've got a solution of sodium chloride in water. It needs to be separated in order to obtain a sample of pure dry sodium chloride. Explain this difference in boiling points in terms of the structure and the bonding of sodium chloride and water, and how this difference is used to choose a method to separate them. Okay. I was fairly grumpy when I was marking these because there were some slightly frustrating answers from some people. Okay, so let's break down the different things that we have got. So sodium chloride. That's a metal and a non-metal. So it's an ionic compound. And we know that ionic compounds form giant lattices. We have got oppositely charged ions. So that's Na plus and Cl minus. We know that there are strong electrostatic forces of attraction between the ions that require lots of energy to break. Okay. Oh, I missed that on the camera. Sorry, folks. Okay, so strong electrostatic force of attraction between the ions that require lots of energy to break. They are ions. They are not molecules. You cannot talk about weak intermolecular forces between ions. You can't have an intermolecular force if the things are not molecules. We need to get our terminology right in these questions because we're throwing easy marks away. You need to learn that an ionic compound has these strong electrostatic forces of attraction. So that's where you have got a positive thing and a negative thing, and there's some sort of attraction between the two of them. It is not a weak intermolecular force. Let's have a look at water. So water is a simple covalent substance because it's two non-metals. So water looks something like that. We have got strong covalent bonds between the atoms, we have got weak intermolecular forces between the molecules. So if I just draw another water molecule here, so let's have some water like that. We've got weak intermolecular forces between the molecules. These are really easy to break. They're very, very weak. Because there's not really any charges involved. So these are weak intermolecular forces because you've got molecules and it's between the molecules. These are strong electrostatic forces. There's no molecules involved. So many people talked about intermolecular forces in the wrong context. So you need to be super careful here, folks. So the thing I need to add on here, so little energy is needed to separate the molecules. And then we also had to talk about our method of separation. So we would use distillation. And you could describe some of the equipment. So condenser or a delivery tube in water, that sort of thing. You need to state that water has a lower boiling point, and then the water could be condensed and collected. Now let me show you the mark scheme here. So obviously we're most interested in the 6 marks. So to get your 6 marks, you had to have an explanation of both of the types of bonding and of the separation technique. And you can see on here it gives you some example answers that would get you 5 or 6 marks. Let's have a quick look at the 6 mark one. Sodium chloride is ionic. The electrostatic attractions between them take a lot of energy to break. Water is covalent. Not a lot of energy is used to overcome the intermolecular forces. Use distillation because water has a lower boiling point than sodium chloride, so water will distill but sodium chloride will not. Water can be collected after being condensed and the sodium chloride will remain in the flask. That is a perfect answer. If you're getting the wrong terminology in there, then you're not going to get all of the marks. And you can see how you're going to get lower marks in here. So simple things like saying sodium chloride is ionic, that's a 1 mark answer. You've only talked about one thing. So I'll leave that on the screen. If you need to pause that and have a look at your breakdown, then you can do. Okay, question 10. So we've got some water sprinklers in some buildings, and the water sprinklers are filled with nitrogen to prevent corrosion when it's not in use. What's the meaning of the term corrosion? 1 mark for reaction of a metal, 2nd mark with oxygen or oxidation of a metal. Would probably get you a mark there as well. Okay, nitrogen is made from sodium azide. It's not a chemical we come across. We don't need to know anything about it. But we do have to be able to do a bit of mole calculations with our gas. So we had to calculate the maximum volume in centimetres cubed of nitrogen produced from 110 grams of sodium azide. We're then going to use our mole calculator. So I'm going to do what I normally do. We're going to write out the equation again, so we've got something to refer to in our calculations. Okay, job number 1 is to calculate the number of moles. So remember, moles equals mass over Mr, which equals 110 grams divided by 65, giving you 1.692 moles of sodium azide. We then had to use our stoichiometry to work out how many moles of nitrogen that we've got. So to go from 2 to 3, we have to multiply by 1.5, okay, to get from 3 to 2. Sorry, 2 to 3. So we're going to end up with 2.538 moles here if we multiply that by 1.5. So there's our number of moles. Then we had to use our gas volume here. So remember, 1 mole of gas is 24 decimeters cubed. We need to find out the volume of that number of moles of gas. So therefore the volume equals 24 multiplied by 2.538, and that gives us an answer of 60.923 decimeters cubed, or if you count in centimeters cubed like it is doing here, 60923 centimeters cubed. And then the final question is a 6-marker. So we're to compare and contrast the properties and uses of pure aluminium and pure copper with the alloys of aluminium and the alloys of copper, and include in their answer the explanation of the similarities and differences in the properties and the uses of a pure metal and its alloy. There's an awful lot to include in here, but I'll try and break down some of the key points. Okay, so first thing that I would talk about is the properties of each of them. So properties of metals, they are good conductors of heat and electricity. They are malleable. They are ductile. So remember, that means moldable, that means stretchable into wires. They are shiny. We could also say that copper is unreactive. Aluminium is corrosion resistant due to layers of oxide. We could also say that aluminium has a low density. So those are all properties of the pure metals. And then we could do properties of the alloys. So they are good conductors of heat and electricity. They are less malleable or ductile than pure metals. And then you could say, you could name some of the alloys. So we looked at magnesium. So that's an alloy of magnesium and aluminium. It has a low density. Or brass, alloy of copper and zinc, it is very strong. So there's some examples there, and you could have picked other alloys. Those are the ones that I mentioned in the mark schemes, but there are other ones available you could choose from. Then we had to give some uses. So aluminium, used for things like cooking foil, food trays. Other examples as well, bikes, be a good example for that. Scaffolding poles is another one. Copper, water pipes, wires, roofing. Again, other things are possibly available there. Alloy uses. So aluminium alloys used in aircraft parts, vehicles, ladders will be good examples there. Copper alloys, things like coins, brass instruments, jewellery, plug prongs, things like that would be also good examples. So here we've got our properties of the metals and the alloys. We've got the uses of their metals and the alloys. We could also give some similarities and differences. So both have metallic bonding, so you could even have sketched your diagram of metallic bonding with your electrons delocalized, and you could label that. They both conduct heat. because the electrons can move. They both conduct electricity because the electrons can move. They both have high melting points. Due to strong metallic bonds. Okay, so there's our similarities. Let's think about our differences then. So in an alloy, the layers are disrupted and can't slide as easily. So you might even have drawn a diagram to show that. You can put a force on here, show it gets harder. Then quite a few people did some very nice diagrams of that. So it's harder for them to slide. This makes alloys stronger. You can also say that alloys can be corrosion resistant. And then you could also give some uses of these again. So things like when we talked about our aluminium alloys, so aircraft parts, they have a lower density, so therefore that's really good for making aircraft parts, or for plug pins we mentioned because they're really strong. You could talk about pure copper is used for wires because it needs to be able to conduct really well but doesn't need to be strong. All those sorts of things would get you your marks in there. Let me give you the breakdown of marks again so you can see how the marks are awarded. So 6 marker, here we go. You had to give one description and one explanation that covers at least one similar property of pure metals and alloys and one difference between them, and 3 uses including at least one metal and at least one alloy. So that's where people dropped lots of marks. There were some quite good descriptions of alloys, talking about why they are stronger, some good diagrams drawn. We missed out on marks by not giving uses of metals and their alloys. You can see as we go to the lower marks, here we've got properties of alloys, similarities and differences, 3 uses including at least one metal, at least one alloy, and an explanation. So that's even to get 3 or 4 marks. If you didn't give uses of metals or alloys or didn't give some examples there, you were sort of limiting yourself into the 1 or 2 mark region, which is why some people didn't do as well on this 6 marker, despite the fact they wrote loads and had some really good chemistry in there. And that brings us to the end of paper 1.